So, hello. So, before starting the second lecture, let's have a quick recap of what we have done in the first lecture. So, we started with the Schrödinger equation, the time independent Schrödinger equation, which is minus h square over 2m del 2 psi x is a function of x only upon del x square, or better you can write as complete derivative also, because this is only one dimensional, plus vx psi x is equal to e psi. We tried to solve this and it gave a result that psi x equals some constant a into basically we had two constants a and b, but we neglected the one of the term. Okay, so this is a e to the power I k x, and then this k was under root 2 me. If you have forgotten this, you can go through the first lecture. Okay, or you are just visiting for the first time, you can check it in the first lecture. Okay, so this is the solution for this Schrödinger equation. Now we proved the second result as that the momentum operator, this px, or simply p for one dimensional case, this is equivalent to minus I h bar del over del x. We showed it how this is possible. Okay, why this operator can be represented as this. Okay, so then we also proved that the commutation bracket of x and px, this is equal to I h bar. Okay, so these things we have proved, and we also proved we also discussed about an important concept in quantum mechanics, that there is no fixed trajectory of the particle, so we cannot find the actual velocity of the particle. We basically find the probability of finding the particle in a given region. So we do not find the term dx over dt, these kind of terms, in quantum mechanics. We can find the expectation value or the average value. Okay, maybe we can calculate, but for a particle we do not find these things in quantum mechanics. So these things we have already discussed. Now the next thing we are going to discuss is that one thing we also missed, that the energy operator is represented as I h bar del over del t, and that's all of the things we have discussed in the first lecture. Okay, so now let's move ahead. So I'm getting this. Okay, so now we can also show that the commutation bracket of E and T, this is equal to I h bar. Okay, so to show this, let's okay, so the commutation bracket E comma T can be written as E into T minus T into E, but this is actually meaningless unless you apply on some wave function. So we will apply it on some wave function. So this will become E. Okay, and basically the thing we are going to do is, first thing we will replace this E by the energy operator. Okay, so let's replace this E by this term. So I h bar del over del t into psi, and because you can see that this is a function we are differentiating with time, so obviously this must be a function of time, x and t. Okay, and then this t minus t into so basically this derivative will go over these two terms, will apply on these two terms, and because this is in the left hand side, so only this E is going to apply on psi. So this is I h iota, basically iota I should call it, I h bar iota h bar del over del t of psi. Okay, so if we can take out this thing common. Okay, so if I take this thing common, then this becomes I h bar, and let's differentiate it with t. So the differentiation of this first term will be del psi over del t into t. Okay, and plus then we will leave the first term psi x comma t, and del t over del t will give you 1. Okay, then minus basically we have taken the bracket already, so this thing is in common, and we will write t over del psi over del t. So these things are cancelling, these two terms, and we are getting I h bar psi x comma t. So we can see that when this commutation bracket acts on this function psi, wave function psi, we get IH bar multiplied by this wave function. So this is clearly evident that we have showed that this E comma T commutation bracket is equivalent to IH bar. Okay, so this is the result we have got. So now let's move ahead. Now let's see one interesting thing, that we will do the same thing in a reverse order. Let's do some inspection to what we have already done. So what we are inspecting, that the total energy E of any system is given by the kinetic energy plus the potential energy. The kinetic energy is given as P square over 2, half mv square, and then we can write it as P square over 2m. So, and plus the potential energy V. Now we know that this P, if you want to convert into operator, or we replace it by their operators, then we can write and apply it on some wave function. We will apply it later, but let's first represent this P as minus I h bar del over del x. Okay. So we can write it as 1 over 2m, then this I h bar del over del x whole square. Okay, plus this, let's we can take the potential term to be 0, or just take this potential term as Vx. Okay. For simplicity, we can also take it as 0, but let's take it as Vx. Okay. So this term will multiply with itself and it will give you iota square, which is -1, and then this h bar square will give you h bar, okay, squared over 2m. Then this term will be applied 2 times, so this will give you del 2 over del x square and then plus Vx. Okay, so and we will replace this energy by I h bar del over del t, and then we will apply the whole in the left and right to a wave function psi. Okay, so we are applying it on some wave function psi, which is obviously a function of position x and time. Okay, so we can write I h bar del psi over del t is equal to minus h square over 2m del 2 psi over del x square plus Vx psi x. Okay, so this is the Schrödinger's equation. Now we can write it in more, I think it will be better if we write it as like this. We take it common, okay, for some reason, because we are going to take the conjugate, the complex conjugate of this of the left hand side and the right hand side, and let's see what we have. Now this is the one dimensional equation. If we generalize this for 3D, three dimensional, we want to write the three dimensional system, then for the 3D we can write for 3D. So for 3D we can write as minus this term, we are writing first over 2m. Instead of this term we will be replacing it by the Laplacian del 2 or the del operator, sometimes we call del 2, and then plus this Vx. V, simply we write it as V or Vx. So now this V will become a function of R. Okay, so I'm simply writing it as V. Okay, then this V, and then psi will now not just a function of x but a function of the position vector r and the time t. Okay, so here also the t is embedded. Okay, so and this will be equal to I h bar del over del t of psi r comma t. Okay, psi is a function of position and time both, and then we are going to take the conjugate of this equation. Okay, so if we take the conjugate of this equation, then this will become minus h bar square over 2m del 2 square plus the v, this will remain same, but this term is going to be the complex conjugate of the psi. Just we are writing the conjugate equation. If we take the conjugate, complex conjugate of both the sides, because it's an assumption now, because we have seen that the solution contained e to the power iota kx, and you know that this can be written as e to the power I theta can be written as cos theta plus iota sine theta. So obviously it's going to be a complex thing, complex function. So there is nothing wrong in assuming that a complex conjugate of this function can exist, and we are writing the same equation for a complex conjugate. For now we are just writing because of the mathematical curiosity, not we are just thinking that it's going to be a physical thing. We have not yet proved it in the first lecture, but let's, because we know that this is a complex thing, so obviously we can take the conjugate on both hand sides. Okay, so this will be psi r comma t equals, and if we take the complex conjugate, this iota will be replaced by minus iota h bar del over del t, and this psi, this asterisk, okay, the psi conjugate and the r comma t. So this is the complex conjugate. Let's give some numbering to these equations, okay, because I think it can go, numbers can increase the equation number. So let's call this equation as equation number 1. Then this Schrödinger's equation we wrote, okay, this as equation number 2, and then what we have got before the conjugation, this is equation number 3 and this is equation number 4. Okay, so now what we are going to do is, this is basically you can think why we are doing this. So this is just because of mathematical curiosity for now, okay, that we can take a conjugate of this and we can do some manipulations, or we will do some algebra with it, and we get that if we take the complex conjugate, okay, of psi and multiply it with this, because you know that any complex number, okay, z, when multiplied with its complex conjugate, sometimes we write it as in mathematics as a bar over it, okay, and in here we are writing as z is asterisk. So these things are similar because in mathematics we are dealing about complex numbers in the complex numbers chapter, and in complex function we represent it as asterisk, so whatever you represent, and this gives you like if is z is a plus iota b, then this z bar is a minus iota b, and if you multiply, this will give you a square, then this will be multiplied with it minus iota ab, okay, then this will multiply with it iota ba, but you know that ab and ba are same things because these are real numbers, and then multiplying iota b with minus iota b gives you iota square, gives you minus, and then minus will cancel with the minus, so it will give you b square. So these terms cancel out and you finally get a square plus b square. So multiplying a complex number or with its conjugate gives you a real number because the iota is missing. Now you get a real number, a square plus b square. So seeing this result, okay, we are basically following the same pattern to get some uh, real value or something related to reality, and that can only be measured using real numbers. So The approach to get a real number is basically multiplying this with the conjugate of the wave function. So keeping that in mind, we will multiply the equation number 3 with psi conjugate. Okay, so when we multiply this with the equation number third, and let's subtract from this, you can see that in equation number 4 we already have the conjugate. So to get some real number, we will multiply with psi. So in equation number 4 we will be multiplying psi from the right hand side. Okay, we take the convention that we will take asterisk from left hand side, and then we are writing like this. Okay, so the conjugate will be multiplied always from the left hand side. So minus the equation number 4, why it is erasing itself. Okay, sometimes it irritates me. And then psi. Okay, so if we subtract these two things, what we are going to get? Let's do some algebra. Okay, so let's multiply asterisk with this term first. Okay, so when you multiply, so this will be in the left hand side, like so. Now let's do some algebra by multiplying the equation number 3 with asterisk from the left. Okay, so if we multiply, I think, okay, so let's do some algebra by multiplying asterisk psi asterisk to the equation number 3 from the left, and multiplying psi to the equation number 4 from the right, and then we will subtract it. So we will do for the left hand side first. So for the left hand side, let's do it. So if I multiply psi asterisk, psi conjugate we can also call, then minus h bar square over 2m del 2 plus v. Okay, then the psi. Okay, then subtract, we multiplied by asterisk from the left, then subtract to the left hand side of the equation number 4. So this is minus h square over 2m the nebula square plus v, and then psi. Okay, I think psi asterisk was already there, so we have to write it like this. Okay, so better we can apply psi to both the terms and then multiply with, I think there is some problem. Okay, so better we can write as psi plus v with an asterisk. Okay, psi asterisk, and then we multiply with psi. Okay, this is the left hand side, and in the right hand side we have this I h bar term is common to both, then from the left hand side we can multiply psi asterisk del psi over del t, leave these things, and the minus term is there is a minus term, but when we subtract it becomes plus. So plus we are multiplying in this term from the right, so this is del psi asterisk over del t and then psi. So this is the right hand side. Now if we for these two terms we can take out h square over 2m minus with minus as common, then we can have psi asterisk, okay, del 2 psi, okay, and this minus minus adds up to give you del 2 psi asterisk multiply by with this psi bracket close, for the v term psi asterisk v psi minus v psi minus v psi asterisk. Sometimes it really irritates me, psi. Now you can see why it goes. So technology gives you some strange behavior sometimes, and there is no explanation why this is happening. I think it is interfering with the Bluetooth of the mouse or anything. Okay. So there is a negative term. Sometimes I forget because it suddenly goes off, and when you are not certain about it. So let's check. So this is psi asterisk v psi, this term psi asterisk v psi, and then we subtracted this term minus v psi asterisk psi, and then we have I h bar, these terms psi del psi over del t plus del psi asterisk over del t, and there is an asterisk, okay, psi. So in the right hand side we can simply say that this is a derivative of the product del psi over del t of psi asterisk psi, okay, psi conjugate psi. And then in the left hand side this is again going, these two terms are basically v is a real thing, it's a real function, so we can take it to the left hand side, and then these two terms are same, so we can cancel these things out. Now we have h bar square. Now if I remember we took a minus sign, okay, so minus h bar square over 2m. Let's change the color, maybe this issue can go. So if I take one of the derivative term, okay, this del operator, to the left hand side and write it as psi asterisk del psi, sorry, this is not del asterisk, it should be psi asterisk, psi asterisk del psi plus this del psi asterisk del psi conjugate into psi, because in computers we call it asterisk. I try to call it asterisk, but this is called as conjugate, okay. So now if you can see, this is looking like some equation of continuity, which is written as del rho over del rho over del t plus, we are calling basically rho, if you take, I think I should write in the right hand side. Okay, if I take everything, let's first take everything to one, either take it to the left hand side or right hand side. So I can write it as I h bar del over del t of psi conjugate psi plus this h square over 2m, okay, del of psi asterisk del psi plus del psi asterisk into psi. Okay, and then we compare it with the continuity equation. Okay, so if we compare with the continuity equation, del rho over del t plus del dot j, okay, equals 0, and this is 0. Okay, so if I compare with this continuity equation, okay, if there is some flow of anything, okay, flow of charge or any material, then we write the continuity equation. This is basically the change in the in anything, any physical quantity, and this is the current associated with the that physical quantity. Okay, so this is the change, and this is anything incoming or going out. If this is positive, then it is being added, and it is, if it is negative, then it is going out. Okay, from a certain reason, if something is coming or going out, okay, so this is basically given by the current or the flow, which is represented by this J, and if something is coming or going out, inside there is some change, and that change is del rho over del t. Okay, and it can be for any physical quantity, like flow of water, flow of current, charge. Okay, so if I compare this equation with this, we can say that this rho is somehow represented by this I h bar psi dagger, not dagger, psi asterisk psi. Okay, so basically this is we should have taken out this if I cancel this term, I can write it in a different manner. If I cancel this h bar with this, okay, we can cancel it out, and also we can divide, because I cannot write directly rho like this. Okay, because the physical quantity cannot be complex, cannot be represented by a complex number. Okay, so directly writing like this can be wrong, so we will take this iota term, we will divide this iota, we can divide the whole equation by this I h bar, and finally we get del over del t, okay, of psi dagger psi. These things are not actually written in the books, because these are already very simple and understandable things. So we can write h over 2 iota m. Okay, we taken this, we have divided, the h bar cancelled out, and this iota, and del of psi asterisk del psi plus b psi asterisk then psi gives you 0. Now we are in the position to write rho as psi asterisk psi. Now this is a real quantity, because when you multiply some complex thing with its conjugate, you get some real value, and then this whole thing, this thing, okay, multiplied by this term can be written as j. So for the j you can write as h bar over 2 iota m into psi asterisk del psi plus this del psi asterisk conjugate, again I am saying asterisk, okay. So this is the current, and we can write the continuity equation. This is the continuity equation. So for if the wave function uh, given by this the Schrödinger equation is representing some, even it is representing some complex represented by some complex function, it can give you some real value. It is giving you some real value, okay, and that real value is psi asterisk psi, and this uh, this can be used to get some explanation of the experiments we do in quantum world, okay. So now we will be writing this continuity equation for one more time, okay. And now from quantum mechanics you know that that this rho psi dagger psi represent the probability of finding the particle in a region, okay. So for any reason you can solve the Schrödinger's equation, and then you can find this rho. This will give you the probability of finding the particle in a given region, okay. So and solving this Schrödinger's equation, we get the structure of the electron, how the electrons are in a hydrogen atom or on helium or other atoms, okay. So we know that the electrons are arranged in s orbit like this, in the p orbit, p orbital like this. So from where this dumbbell shape or for the shape of d orbitals we get, only by just calculating this rho for the different potential of the system of the particles consisting an atom, okay. So this can be a very tedious task. We can do this in some quantum mechanics class, but we are here interested not in finding the shape of the orbitals, okay. This can be done, although this is a very very challenging and very interesting problem of quantum theory, and basically all of the chemistry can be explained on the basis of this Schrödinger's equation, okay. So Schrödinger equation is the key to all the chemical reactions happening, where you find how the bonds in a compound exist, like the coordinate or the covalent bonds, how Schrödinger sequence help you describe the shape of the orbitals for an atom by only by solving the Schrödinger equation for the potential of existing inside an atom or in a compound. We can find the shape of the molecule, the shape of the bonds, okay. So this is another world of doing the things, but we are going into the meaning of these things basically. So you understand that this row basically represents the probability of finding the particle it is associated, but we will call that this is some real quantity which is given by the Schrödinger's equation. Okay, so now let's do one thing. Let's recap what we have done. We have written that the energy is given by p square over 2m, and then v, the potential energy. This is the kinetic and potential energy. But this energy is valid for a particle which is moving at some velocity much less than the velocity of light. Now you will call me that we are not calculating velocity in quantum mechanics. We know that dx by dt, these terms are missing because the particle has a strange behavior. It is not following any specific path. It has no well defined trajectory. But we know that although the particle is moving, it can disappear from here and directly present here. Okay, particle can go anywhere, but we know that even if it is going anywhere, it is not going at a speed similar or equivalent or anyway closer to the speed of light. Okay, it is very less, because the energy expression we have used is this. But you know that the particles, even if it is moving inside atom, can have very high particle, or I should say electrons can have very high velocity. Okay, and this equation is for the classical world. Okay, where a ball or a projectile is moving with some velocity, then we can write the total energy as kinetic plus potential. But for a particle like electron, this energy expression cannot be always correct. Okay, so you know that if you have gone through the theory of relativity, the energy of a particle, of a relativistic particle, a particle which is moving in the positive x direction with some velocity which is not equal to the velocity of light, but it is not much less, only less than the velocity of light. You can see the terminology here. This is much less than the velocity of light, but it is less than the velocity of light, or it can be comparable to the velocity of light. So for any particle which is relativistic, by relativistic I mean the velocity is somewhat higher, but it will always be less than the velocity of light. So E, the energy expression cannot be written like this. So what is the expression? This is E square is equal to P square C square plus M square C to the power 4. Okay, so let's see what will happen if I replace the terms E and P with the operators which we defined in our theory from the time in this continuing second lecture. Okay, so if I represent E by I h bar del over del t, okay, and P by minus I h bar del over del x, just we are doing for one dimensional. Okay, first, so we can write this thing squared. Now we can also directly write it for the three dimensional, because we have already done for the three dimensional. So this will be squared. Okay, and obviously we will apply it to some wave function psi. Okay, will be equal to this p square term will be now, because we know that the p operator is represented by minus I h bar del for three dimensions. Okay, so we can write it as minus I h bar del whole square, and this psi, okay, and then c square plus this m square c to the power 4, and this basically this whole thing is being multiplied to psi. I think I should write it like this. Okay, then this is being applied to some psi. Okay, so now we can write it as I square terms is minus h bar square del 2 psi over del t square is equal to this iota square it will give, and this will be minus h bar square del 2. Okay, and this c square we can take to the left hand side. Okay, so let's write it clearly as h bar square, okay, c square del 2. I forgot this term, this symbol is also called nebula sometimes. Okay, or sometimes it is called del, so nebula square you can call also. Okay, plus this term m square c to the power 4. Okay, and then everything inside the bracket and then psi. Okay, so this is what we have got. Now if we take everything to one of the side, either let's take it to the left hand side, and we can cancel out this minus term. Okay, so h bar square del 2 psi over del t square plus, okay, this is not plus, I think. Okay, yeah, this term can be a negative term, so minus h bar square c square nebula square. Okay, this time I called it nebula, so plus m square c to the power 4. This will go to the left hand side and it will become, I have taken this term to the right. Okay, I have taken this term to the right, so it will become positive, negative, and this is already positive, and then this is the whole term is being applied to psi equals 0. Okay, so this is what we have got. Now we can divide the whole equation by this, and let's see what we get. So this h square will be gone, and we can get 1 over c square del 2 psi over del t square minus del square or nebula square plus m square c to the power 4. And now we have cancelled out two terms of c, and we get over h square acting on psi gives you 0. So this is what we get. So I think I should give some numbering to this also. Let's call this equation as equation 1 and this as equation number 2, and we can also write it in some interesting way by, if you have any time gone through theory of relativity, they call it as the box operator. Okay, so basically this is written as the box operator squared. Okay, second 2 times it is acting, then it becomes the square of the box operator plus this m square c square bar square acting on psi gives you 0. So this is how written in this thing is written like this. So this is how we have written the some kind of like similar kind of how we derive the Schrödinger equation from the classical energy equation E equals p square over 2m plus v, and in the similar manner in the same we are following the same recipe here by starting with the Einstein's energy relation or relativistic energy equation, and then we have got this. Now this is some elegant way of writing the same thing, but we are interested in this here. Now if we do the same thing, if I multiply, call this equation 3, if I multiply a conjugate, write the conjugate equation for the same equation 2 as we have done for the Schrödinger's equation. So for that we can write as 1 over c square del 2 psi conjugate over del t square. I think there is a mistake. I have written this psi here. I should have erased this psi, okay, because we have taken it common, so I think this is not required, okay. This, so now after correction we have 1 over c square, applying, take this thing also, take out this thing. So now minus del square plus m square c square over h bar square, okay. So only this thing is going to be the conjugate equals 0, okay. So let's call this equation as equation 4. So now what we are going to do, we will be multiplying psi conjugate to equation number 2, and then we will subtract this multiply this conjugate equation with psi, and then because in the right hand side we have 0, so it must be 0, okay. So let's subtract these things. So if I multiply this from the left hand side, okay, better I think I should write it collectively, then it will be better, okay. So for this term, for this term, okay, and this term, we can call it as 1 by c square, okay, and then multiplying psi star, and then this term, del 2 over del t square, del 2 over del t square, then the psi, okay, minus this term 1 over c square, I think this is not asterisk, this is multiplication sign, okay. So del 2 over del t square and multiplied, there is some asterisk, this is acting on this, and then multiplied by this psi. So this is for the first term of the left hand side. Then we have the second term, this nebula square. Then we have plus, I think it should be with a minus sign, so minus this minus psi asterisk, this for the second term psi asterisk. There is a better way to do this. If I write this thing collectively. Let me do like that. Okay, so first let me do in a better way. I think people may get confused with it, so I have to write a little bit smaller for this. 1 over c square del 2 over del t square minus del square. Okay, so the thing I'm going to do is I'm multiplying by psi. Okay, I am writing equation 2 basically, equation number 2. Okay, these things basically hang and sometimes it creates a problem for me. Yeah, this equation plus m square apply on psi m square c square by h square bar square psi equals 0. Okay, and then 1 over c square del 2 psi asterisk over del t square minus del square psi conjugate plus m square c square over h bar square psi asterisk. Okay, equals 0. So this is equation number 2 and this is equation number 4. I have rewritten these things. Now we are multiplying psi asterisk from the left and we are multiplying psi from the right. Okay, and then we will be subtracting. So then we are subtracting. So now we can clearly write it as 1 over c square, 1 over c square taking common from these two terms, then psi asterisk del 2 psi over del t square minus del 2 psi asterisk over del t square and multiply. Not, this is not asterisk. Okay, this is not asterisk, but it is simply a multiplication. Okay, so now this is multiplying from the right, then we have written psi. So this is for these two terms. Now let me close the bracket. Okay, these terms are be done. Now for the second term we have negative of psi asterisk nebula square psi, and this minus minus gives you plus psi asterisk del square. This is multiplying from the right. Okay, so we have this nebula square psi asterisk psi conjugate basically and psi. So now we have the second term written, and plus now we can see that these two terms can cancel, but let me write it: m square c square over h square and then psi asterisk psi minus psi asterisk psi equals 0. Okay, so now what we have is 1 over c square. Okay, so we have psi asterisk del 2 psi over del t square, and we have minus, I think this is 2. Okay, del 2 psi asterisk del 2 psi asterisk over del t square psi, these two terms. Okay, so we can collectively we can write it. Okay, but let's write this thing together for some time. Minus psi asterisk del 2 psi plus del 2 psi asterisk to psi equals 0, because these two terms will cancel out. So now we have written so now we can write it as 1 over c square psi conjugate del, we can take out the one of the derivative term in the left hand side. Okay, so let me write like that. So 1 over c square del over del t. Okay, then this will be the single derivative del psi over del t minus, for same for this, and we can take this to the left hand side also. Okay, because you know that z into z asterisk is equal to z asterisk z. Okay, so we can write it like this: psi into del psi asterisk over del t. Okay, and now this has become the first derivative because we have taken out the derivative term, one of the derivative term outside, and minus instead of minus. Okay, we can take it as positive also, but let's, for the time being, we can write it with a minus sign. Okay, so psi asterisk del. Okay, we can take out the del, the nabla term. It's doing the same thing here. Better, we can take out the del term outside of it. Then we have psi asterisk del psi, and this minus with a minus sign because this is minus. So del psi asterisk. Okay, and it doesn't matter where you write this, to the left or to the right, so we can call it as like this. If we wanted to reduce one of the bracket, then we can write it as this: psi del. Okay, so this is 0. Now the equation is going to, let's see if it is going to match with the continuity equation. So what is continuity equation? We have del rho over del t plus del dot j equals 0. Now let's find the similarities in this. So the j term can be the negative of this. Okay, and let's see what we have for this row. So for this row we can have this term. Okay, but with 1 by c square including. Now if you previously go and check the j term. Okay, let's go back and check. Previously we have seen that for the Schrödinger's equation this is the j, and let's write this j here. Okay, so the j we have is from the Schrödinger's equation is h bar of 2 I m iota m psi asterisk psi minus del psi asterisk psi. Okay, so this was the term, and let's compare it with it. do we have this term here? Okay, we actually do not directly have this term, but with this thing is multiplied with it. So better we can multiply the whole equation with this term and call it, then we will be able to call it j. Okay, so if this is multiplied to the whole equation, then this will become j. Then what will be the value of rho? In that case, the value of rho will become 1 over c square multiplied by h bar over 2im, okay, multiplied with this whole term. So psi asterisk psi conjugate del psi over del t minus psi del psi asterisk over del t. You can check it you can check it by just multiplying this whole term, this h bar, which we got from our previous calculation of the Schrödinger's equation. So this h bar over 2im, if you multiply this to the whole equation, you will get that this will be multiplied. And let's consider the same j which we have seen previously. So the new row will be this 1 over c square multiplied by this term, okay, and then this. So you can write the row as, but there is a difference also. Let's see that there is a negative sign here, but actually in the continuity equation there is a positive sign. So I should change this these terms. Okay, so this is I think there is some mistake in writing this. Okay. So maybe I think there is some mistake in writing this. This term should be in the bracket, okay, or we have already written, okay, we have written it from our previous, okay, this equation, yeah, this one. So you can take this side toward the left and right like this. Okay, so that is we have written here. So now if this is j, then the row will be this, and we can, because of the negative sign, the j can be written as a negative of this. Okay, so finally we will be writing j as let me remove these things. J will be equal to, okay, h, if I take the minus sign, it will be minus iota, and we can take it to the, you know that 1 over iota is equal to minus iota. So we can take the minus sign and write it as iota. So this will be I h bar, okay, over 2im, but we wanted to write it like that. Okay, so better you can write it as, you can write it in any manner, del psi minus psi del psi. Okay, this is the j, and now this should be removed, this iota should be removed. I should remove this and write it as 2m. So this is the uh, the j, and the row will be written as, now the, because we have taken out a negative, it will be better if we can take out the negative sign also from common, then this will be our j, and there will be no need to, let's do this. Okay, uh, if there is some plus sign, there will be a minus sign, and then this will become directly the j, so there will be no need to take this iota term in the top, and this will be 2 iota m. Okay, this will be 2 iota m. So this is the j, and then the row will be with a negative sign, and this negative will go inside, or you can take it to the top. So I h bar over 2 m c square psi asterisk del psi del t minus psi del psi conjugate over del t. So this is the row. Now sometimes this is also called as the charge, okay, because we write it for in continuity equation for charges also, then this physical quantity may be referred as charge. So now if we compare the row of we already compared the j, the current density, and this is almost same for both of the cases, but when we compare the charge or the row for the Schrödinger's equation for non-relativistic case, for the non-relativistic case, we see that this is the okay, where it is, yeah, this is j and this is the row. The row is basically a real number, is a positive, it will give you a positive value. Okay, better positive, I should call it a real value. Okay. And but if I come here and see the row, okay, the charge density, you can see that this is not like psi dagger psi. There are basically two terms. The derivative of time is involved. Now one thing is missing. I think I should have stated it previously, that this equation is the equation number 2 or 3 is called as Klein-Gordon equation. Klein-Gordon equation. These, either you call it the second or the third one, or the conjugate equation. So basically this equation is called Klein-Gordon equation. So basically we are trying to find the solution from the Klein-Gordon equation, right? But we have derived it from the relativistic energy expression by replacing the energy and momentum momentum energy E and the momentum P with the corresponding operators. So now if we closely observe this row, then we find that this row, okay, this involves a derivative term first, then that means it is time dependent. This is not basically it is giving you a constant value, rather it is time dependent. Secondly, this can be positive or negative. Okay, this can be either positive or negative depending on which term, this term or this term is greater. So so this implies rho can be either positive or rho can be negative. But if you see that the rho basically represents here the probability density, and the probability of any particle, probability of finding any particle, if the particle is present somewhere in the space or the volume of the space we are considering, can never be negative. It can either be that there is no particle, but it can never be negative. But here the probability density is can be negative. So because of this reason, Klein Gordon equation, or the how the equation which derived after which we derived after quantization of the relativistic energy expression cannot be the cannot express a real it cannot be accepted as as the quantization of the energy quantization for a relativistic particle. Okay, so Klein-Gordon equation was not accepted as a wave equation for several years until Pauline Vyskov reinterpreted it as a field equation like the Maxwell equation. Okay, so we will come to the Maxwell equation later, but after that Dirac tried to quantize this equation, the relativistic energy equation, in a different manner using the matrix method. He basically wrote it in some matrix notation, and then he got something which is relevant, which was accepted as the wave equation, and this anomaly was actually removed. But apart from this, the Dirac equation resulted into some strange entities, and it indicated the existence of antiparticles. So in the next lecture we will be dealing with the Dirac equation, how Dirac was able to write the energy expression in a manner so that it not like the Klein-Gordon equation which gives you a negative charge density, okay, negative probability density. Okay, so we will see in the next lecture.